Tuning in. The title slide here covers some of the topics. I'll try to use the mouse cursor to help guide you to some of the points throughout the talk. The earthquakes, this iconic photo from the 2018 Anchorage earthquake is shown in upper right. Bears shown at lower right here, standing on top of one of our seismic stations in central Alaska. And the high performance computing comes in and trying to obtain snapshots of the seismic wave field, such as shown here at left. I'll say welcome to Fairbanks, Alaska, at least via remote participation, and I want to give viewers a sense of this place before we talk science. So it's winter here. This is the forecast, and as I wrote down here, it is sunny with a 100% chance of jogging with the West Ridge runners after this talk. In my view, you can dress for too cold weather, and you can't do anything about too hot weather. So this is some of our running group from a couple weeks ago. If we look up in the night sky, there's also an aurora forecast every day here. Last night, the forecast was low. It was 2 out of 9, shown here at the right. Nevertheless, you could see this if you looked up. This shot was taken from some webcam about 8 hours ago. People always ask me about the aurora, so it's worth mentioning this has happened last night, for example. And to give some other better idea of where we live up here, other nights are more dynamic. This is a few shots taken a few minutes apart. The night sky is vibrant, it's colorful, it's a pretty neat place. So at this moment, there are many seismometers hard at work all over Alaska, faithfully recording ground motion and whatever else is happening. So we'll look out here. This is a seismic station out in central Alaska. See what kind of stuff is going on. You can't see it because it's under the snow, but some of these things are maybe not intuitive if you don't live up here. That's a cat, that's a lynx walking around in the winter. There's another one. Not the kind of thing that you see in more populated regions. Here they are again in a storm. There's 3, there's a bunch of them. So this gives some idea. This is wintertime in Alaska. In fact, this shot was taken about 3 years ago on a camera at one seismic station. There are other things about Alaska, as it says here, where people shoot moose and highway signs. This is Kyle Smith, a PhD student, en route for some field work and outreach opportunity. The sign is not that legible, but for us it means a lot because this is the Transportable Array Station 120 I-23K in Minto, also the upgrade site AKMLY. And this is Kyle Smith, who's done his PhD work involved in one of these projects and will be featured later as well. The outline of my talk is shown here. We'll come back to these points. It's roughly in chronological order, trying to showcase some history of seismology in Alaska, some ongoing projects. My goal is to convey the space and time scales of earthquakes. We use these simulations to get some idea of how big, how long, how strong earthquakes are. And at the outset here, I'll say that my target audience is scientifically curious undergraduate students. That's who I'm talking to. There'll be some review for many of you, but that's the target. So we're going to start at plate tectonics. Here's a map of the world. We've got a lot of earthquakes. Earthquakes give us a picture of how we divide the Earth into plates. So there are the plates. We are right up here, northern part of the world on the North American plate. It's easier to see these plates when we put the continents on top of them. Again, I'm going to keep showing where we are being broadcast and featuring this talk from up here in central Alaska. Here are the plates of North America. There's one other thing we need, is that we need to describe the motion of these plates. So this shows the motion of the plates on the planet relative to, in this case, North America being fixed. So what we see is that the Pacific plate is moving to the northeast at some, the scale bar shows 200 millimeters per year. At some centimeters per year to the northwest, it goes subducts underneath the Aleutian Alaska Arc. And on the southeast boundary of Alaska, it's more like a San Andreas style boundary of a right lateral strike slip fault. So there's our setting for Alaska plate tectonics. And earthquakes are a consequence of plate tectonics. And there are lots of earthquakes in Alaska. This shows a USGS map kind of highlighting some of the major earthquakes that have occurred along the Aleutian-Alaska boundary. This shows the megathrust here, the other plate boundary being the strike slip boundary in the southeast. In between is a collisional zone near the Wrangell St. Elias. And we see some of these larger earthquakes like 1964. You have the Denali Fault here that broke into 7.9. We'll discuss that. Fairbanks is right here in interior Alaska, and there are large earthquakes all over the place. If we go to 1 year of earthquakes, 2018 was a spectacular year for earthquakes. 55,000 earthquakes in Alaska, and this shows a snapshot of what happened in 1 year. So Fairbanks is right here in the center. What you're seeing is the signature of the downgoing Pacific Plate shown by earthquakes for just 1 year. We also see here in this year, we had magnitude 6 earthquakes in Kaktovik, far, far from the plate boundary up here on the north slope. All the oil reserves, the Arctic National Wildlife Refuge is in this region for reference. A magnitude 7.1 earthquake in Anchorage on November 30th, 7.9 earthquake offshore Kodiak, January 24th, and then your typical run-of-the-mill magnitude 6 Aleutian earthquakes that pretty much go on without much notice year by year. But this shows a picture of Alaska. It's an exciting place to study earthquakes and record them. And in terms of the earthquake counts for the US, many seismologists are aware of this, but maybe not the general public. Alaska counts for 84% of the magnitude 4 greater earthquakes. This is in the past 5 years. You can look at a century. You can cut the magnitude how you want it, but for large earthquakes, Alaska counts for the majority of events in the US. Another comparison, this is kind of an odd look at this seismicity in Alaska, but what we're looking at here on the left is Anchorage, Fairbanks. It's an oblique view of the eastern end of the Alaska subduction zone, looking at earthquakes within the downgoing subducting plate. So one point just to emphasize about Alaska is that in the plate that's being subducted under Alaska, there are lots and lots of earthquakes. And this is relevant for using them for understanding earthquakes within the plate, such as the 2018 Anchorage earthquake was within the subducting plate. But it's a different scenario, for example, than offshore. This is Washington, Oregon, and California, where you have the Juan de Fuca plate subducting, and certainly an extreme seismic hazard in both places, but in terms of the activity going on within the plate, it's pretty quiet in Cascadia relative to the deformation in terms of these intraslab earthquakes. So that's another sort of distinction of Alaskan earthquakes. All right, looking at from 1904 to present, the growth of the permanent seismic network in Alaska. This will be just a couple slides to bring us up to date. At the time of the magnitude 9.2 Alaska earthquake, there were 2 stations in Alaska. One in Sitka, installed in 1904, and one in Fairbanks, installed in 1935. This is a cool image from a 1936 BSSA paper describing the installation of this seismometer. So there were 2 in Alaska for this 9.2 earthquake, the second largest ever recorded on the planet. Fast forward 50 years from 1964 to 2014, we obtain an impressive broadband network for earthquake monitoring, but still some holes in the coverage. Here's one of those holes. It's the size of California. And what you see here is that in this region, first of all, there's no roads, so there's no way to easily get to this region. And there's also been 3 magnitude greater than 7 earthquakes within this region. And so this sort of was a reminder of the value that we could achieve by putting some stations out here, scientifically understanding what's going on in this active tectonic setting. And this was achieved. So I describe the deployment of the EarthScope transportable array in Alaska as a monumental achievement by IRIS, National Science Foundation. It's not something that any one PI could hope to achieve. It's a real amazing coverage of stations here, and this is what it looks like right now. So just to show this in another form, If you go into IRIS web services, they've got tools where you can just say, show me all the stations in the data archive at this moment in time. Here it is in 2014. This is a large chunk of land out here with no seismometer, and makes it hard to understand what's going on in earthquakes in the region and to image the structure. Here it is now. So all these dots are stations live right now, and so it's just a golden era for seismology in Alaska. In addition to this, if you look at, this is on June 1st, 2016, if you look at what's available, there are several temporary experiments simultaneous with the deployment rollout of the EarthScope transportable array. These are shown here, this flat stations in interior Alaska we'll look at, salmon in the Cook Inlet region of Alaska, this wolf project in the Wrangels, McKinsey Mountain EarthScope project. So these kind of literally fill in the holes, going after certain scientific targets, and I'll be featuring some of these in the talk. You can see at this moment the transportable array was not fully rolled out in the western portion of Alaska. I also want to identify the Alaska Amphibious Community Seismic Experiment. This is kind of unprecedented coverage in the Kodiak, Alaska Peninsula offshore region of ocean bottom seismometers, getting out toward the sections of the subduction zone where the plate boundary is that we really have generally have poor coverage just due to lack of land. And so this is a large experiment between 2018. You can check out an EOS article and online sources, ABERS and others, to see more information on this. And these data sets are open to enhance the land-based acquisition. 1964 Anchorage earthquake. I should show a couple motivating slides here just to give a picture of what happened during this earthquake in Anchorage. These are some iconic photos, Government Hill Elementary School, Turnagain Heights subdivision at right. You can see these homes tumbling toward Cook Inlet here. This is really the spectacular deformation that can arise when the ground fails due to liquefaction. So the shaking is felt throughout the entire state of Alaska, but in localized regions, and especially in urban regions where there was ground failure, the homes on top of this liquefied soil were extremely deformed. And one more photo to show this, sort of a larger view. You can see the homes in this image shown here. Basically, there's this liquefaction and this land slid out toward the lower left, which is Cook Inlet, the ocean at lower left, and you had this run out. So you can see the contrast of the kind of deformation also that can occur from this home versus this one. Seems to be kind of the unluck of the draw, but a reminder that the local site conditions are extremely important when being fed with magnitude 9 minutes of ground shaking. So we can look at this earthquake, even though we don't have seismic stations in Alaska at that time, or 2 of them to record it. We might want to take our best information about the structure of Alaska and the information about the earthquake source, which lasted several minutes, to look at what this wave field might have looked like. So this is an oblique view with Anchorage here, Fairbanks on the right. This is Kodiak, and at this moment, 3.3 minutes after the origin time, the large slip that was occurring at Kodiak is happening at this moment in the simulation. And so by seismic wave field, we're talking about here at a fixed moment in time at the Earth's surface. This is a picture of the seismic wave field. So how do we get there? Seismology is about solving the wave equation. And on paper, it doesn't look so bad. There's not that many equations here. We're talking about solving the equation of motion. What we need for that is we need to describe the Earth structure shown here in red. That would be the density at every point in space. That's rho. And we need to describe the elastic tensor at every point in space. That's this c. You could think of that as compressional wave speed and shear wave speed if you want to reduce the elastic tensor to an isotropic case. We also need to describe the earthquake. That's this F shown in blue. It's got hypocenter at XS, and it has some time dependence. We need to describe the earthquake in order to see the wave field. And the goal here is the green, which is the wave field. It's a vector field at every point in space, and it varies as a function of time. We also make use of this Hooke's law, so this relationship between stress and strain shown here. This is the information. This is the problem we're trying to solve. And so the question is, what makes this so hard? What makes it so hard is, as any geologist or even layperson might tell you, is that the Earth is a really complicated place to describe. We're going to have to describe all the intricate details of the Earth to a computer. And in order to do that, this problem gets very challenging to solve. So here's a picture of that, and this is where gets shown as an example for taking the entire planet. You're going to slice up the entire planet into small domains. You're going to feed each one of these small domains to a computing core in a large computing system. This one was an older picture from University of Alaska Fairbanks. And at each time step, you solve the wave equation and you have to share information with all of your neighbors. And by doing this, you distribute the memory of a very large problem across a large number of machines, and you can solve wave propagation in a very complicated medium. So the codes we use are these open source SpecFem 3D software that have been around for about 20 years now and are always in a sustained state of development. So that's how we break up the problem to solve. We also have to describe the Earth, and this shows a little chunk of a mesh, a finite element mesh of a section of Alaska. Looks like we have this sort of varying block sizes, and that's done to make the most of the compute power that you have. So as wave speeds get faster down in the Earth, you can get away with having larger blocks without losing any accuracy. And this is a way we try to be efficient with the simulation resource we have. On to the Denali earthquake. 2002, magnitude 7.9 Denali earthquake. If we look here in Alaska, this is again Cook Inlet. We say, where's the fault here? And you can see maybe from looking at this why even in the 1920s, flying airplanes over, USGS geologists could tell this was one of the major fault systems in the world. And hopefully with the cursor, you can see this rainbow-shaped strike going in here. In 2002, this fault broke out on the eastern portion here in a magnitude 7.9 earthquake. The one highway going north-south, crossing the fault there, shows a max offset of 2.5 meters here. Along the fault, there's actually 8.8 meters. We have this sort of textbook side offset from this earthquake. You also had spectacular landslides. This is the Black Rapids landslide, shaking of the mountainside here. All this material went across this 2.5 kilometer wide valley, which should be white. It's a glacier. But you can see these landslides shook free as the Denali Fault rupture came right underneath this glacier. So just sort of a spectacular example of shaking effects in the setting in Alaska. Same view here looking east of what happened in 2002. Fast forward to 2019, this is 1 year ago, pretty much to the day. We deployed 400 nodal seismic stations on the Parks Highway. And here, this project led by Amir Alam, Kevin Ward, and me involved sort of two different scales of experiments. Amir, the leader, is very dedicated to the job here. He's shown in a pilot project, 2016. This is what these sensors look like. Undergraduate Nick Locke in this setting. This is actually on the Richardson Highway. Amir is really dedicated to the subject matter. This is that's the Denali Fault mechanism there. So we were the lead. He was the lead on the project, and we had two targets. One was a 300-kilometer line from Nenana to Trapper Creek. These colored lines are the Slab 2.0 subduction zone contours. So we're overlying a downgoing active subducting slab, and these are actual dots here. So there's 300 or so dots along this line, and there was another zoomed in line 3 kilometers long crossing the Denali Fault. So the spacing here of somewhere 30 meters, but more like as small as 3 meters across the actual fault. We had sort of two simultaneous experiments, both of them centered on the Denali Fault, shown here crossing at Cantwell. This shows, if you look on the right in LiDAR, a really spectacular view of this sharp lineament that is interpreted as the trace of the Denali Fault. There's a paleoseismic study by Sean Bemis and others in this region as well. And this ridge is pictured at left of us standing on the steep ridge in the conditions that we had, which frankly were a lot warmer than they are today. So we were lucky on the weather last year. This shows definitely happy graduate students that are helping with this deployment. We have these sleds pulling up and down these compression ridges that you have associated with large strike slip fault systems. And this shows the boxes getting to the sites, snowshoes, kind of unorthodox conditions, but that's optimal for the scientific data that we're looking at. Onward to the south with the salmon deployment between 2015 and 19. This shows sort of the tectonic elements to frame some of these discussions. We have the 1964 aftershock region, hundreds of kilometers long, up against this Cook Inlet sedimentary basin. It's where oil and gas was discovered in 1956, 1957. And what we have, this large sedimentary basin, A is Anchorage, Spur Volcano, Redoubt Volcano, Augustine Volcano, Fairbanks. This is the inferred subsurface outline of the Yakutat Pacific thickened crust that is being subducted here in the offshore region, but it's inferred to be underneath this section of Alaska in the subduction zone. So the Salmon Project looks at a profile of stations across Redoubt Volcano. And one of the motivation here, you can look at data from an earlier project where if you have an earthquake in this region north of Anchorage and you look at seismic recordings in the deep part of the station's basin here in Nikiski, Soldotna, you can see from west to east, there's higher amplitude, longer duration shaking. So data supports this. We have a much more extensive view of this now that this project is over, but the basic idea is that the basin can amplify and sustain ground motion. This shows the deployment. The magenta stations are shown here, the stations we deployed. The contours are the basin contours. This field effort was led by Doug Christensen, Melissa Driscoll, and me. Southern Alaska Lithosphere and Mantle Observation Network. Some of the challenges, this photo highlights some of them. Looking at Western Cook Inlet, there are huge tides. We're driving a three-wheeler with a trailer into this boat in a rock garden. It's kind of a nightmare for a boat captain. Bluffs that are fairly hard to scale. So we had challenging field conditions to get to these remote regions, and we didn't fully understand the scale of the challenges with regard to the animals out there. But this is Doug Christensen and Neely at an install on the eastern side of Tustamina Lake on the Kenai Peninsula. This is what it looked like 12 days later, at least according to when the data went out. And so a bear here just came in and demolished everything. This is what we found the following year. So clearly data loss and trying to figure out how to minimize these effects. Another example from the project, a helicopter site off the flanks of Redoubt Volcano. This is as we found it, boxes pulled out of the ground, torn up, batteries are dragged off somewhere on the tundra. And this is clearly a pretty disappointing scene to come to and made us start thinking more about this issue. Scientifically, we found some very exciting things regarding the basin amplification, and this shows a recent study by Kyle Smith at UAF, and this just shows the kind of coverage we had with station coverage of the downgoing subducting plate. So this is a 1-to-1 profile. We have a lot of stations in this back arc region, which we previously did not have. Here's the basin at 1-to-1. Doesn't look that spectacular at this scale compared to this downgoing plate, where we can use earthquakes to illuminate the basin and other features. If you enhance the topography and vertical scale, what you see is that the basin is much deeper than the mountains are on either side. And if you've been in Cook Inlet and you look toward the Kenai Mountains or Redoubt Volcano, these are spectacular, tall and interesting features to look at. So next time you're down there, imagine just how deep this bowl of sediment is and what it's doing to the seismic wave field. So you can see the coverage of stations we have in the basin. So here's a picture. During this project, we had a magnitude 7.1 intraslab earthquake. And here's a picture of that. I'll probably play this twice. You can see a time bar. This is half minute in. There's the P wave out front, fairly weak. And here comes this S wave really wrapping itself into the basin. This is the Kenai Peninsula shown here. I'll just launch that one more time. Remember, it's 100 kilometers or so deep, so it takes a while. It takes a while for the waves to reach the surface at all. So here we are, half minute in, the P wave reaches Homer, and then comes the S wave. And so the simulation suggests that shaking is expected to be stronger on the Western Kenai Peninsula, and that's true in a lot of historical earthquakes. There are strong shaking effects on the Kenai Peninsula where you have these deep sections of the basin. I pulled this from the New York Times snapshot on September 19th, 2017 for the magnitude 7.1 earthquake in Mexico City. There you have millions of people, but the fact that you have a simulation from an intraslab 7.1 earthquake on the front page of the New York Times, it's a reminder there's societal relevance to this information, both in terms of the data being recorded, what people felt, and also the simulations that can sort of inform us and try to understand what kinds of shaking might be expected for different earthquakes besides the one, for example, this one here. On to Central Alaska, looking at the flats deployment from 2014 to 2019. Now we're looking at the interior, so intraplate tectonics of Central Alaska. Here's a cross section from the trench, something like 800 kilometers inland. F is Fairbanks, N is Nenana, M is Minto. Minto is a small native village. Nenana is a town on the Parks Highway, and we're looking at sort of just north of the limit of the subducting slab. So here's a cross section showing along that way. You have the trench, Nenana, Minto. A lot of these events we're looking at are deep in the crust, something like 20 to 30 kilometers. The crust is expected to be about 30 kilometers there. You have the Denali fault here. So this just gives you an idea of the setting for this next set of slides. Classical picture of this setting is called bookshelf faulting. I think it's a good model for trying to explain relative sense of motion. And what it is, if you take a stack of bookshelves and you tip it, you shear it to the right, the relative motion between each book is left lateral. The shear zone is right lateral. The relative motion between the books is left lateral. And so that's the setting invoked here in this 1995 paper. You have the Tintina fault zone, a right lateral fault system, the Denali fault, right lateral fault system. Then you have a lot of these smaller faults in between that are inferred to have left lateral faulting as this thing rotates to the right. So it's a good picture. It may not be entirely accurate. There's a fold and thrust belt to the south here, but I think it works pretty well for keeping track of the scale of the different strike slip fault systems. So here we have semi-cartoon view of this Caltag Tintina fault system, Denali, and then we'll be zooming in here on one of these left lateral fault systems, the Minto Flats fault zone. If we zoom in on that system, it turns out there appears to be two fault strands, at least from the seismicity. There's no surface expression, but the seismicity suggests there are these two fault strands, and in between these two left lateral systems, you have a gap here, and classically, the inference is that this is kind of a transtensional setting where in between these two separated fault strands, you would expect there to be opening. And there is opening, it appears, in the sense that there's a large, deep sedimentary basin shown here. This is two independent data sets, the seismicity lineament here aligned with basin depth inferred from gravity and magnetic airborne data. And so this shows basin depths here of up to 7 kilometers. And when we look in detail at the style of earthquakes occurring along this boundary, we see that these are dominantly strike slip faults, including a magnitude 6 left lateral fault here in 1995. So when we look in detail, not only are there lineaments, but they seem to be consistent with left lateral faulting, including, for example, a normal fault on here. So when we look at earthquakes in this fault zone, it's a moment to step back and say, what can you do with the simulations? I like to kind of highlight a couple things. If we look at a snapshot for an earthquake, this is a magnitude 5 just north of the fault zone. There's P and S waves. There's also surface waves that follow the S waves. You can look at the polarity of the P wave. So for example, it goes red, then blue in the far left. Here it goes blue, then red. That's a reminder that there's sort of a radiation pattern of the first motions shown. S is the largest amplitude. You can see that. We know that. There's an influence of the basin. You can see the basin kind of starting to really distort the wave field. There's the influence of topography. P wave reaches Fairbanks in 12 seconds to give some sense of time between when this earthquake starts and when people start feeling the shaking. So this gives some sort of guide for what things you can look for. I'm going to show 3 simulations of earthquakes that occurred in this region, starting with this one. And it's all the same model, but the idea is that the basin influence depends strongly on the excitation or the kind of the earthquake. So I'm going to kind of jump ahead here to the next one. Here's an earthquake right under the basin. It's quite a different picture. You see the P and the S wave going outward. And if we look to the south here, this is kind of near Clear Air Force Base. We have an earthquake coming up from the south. You've got this sort of wave effects that are quite different. And in all cases, a lot of the wave field is trapped within this sedimentary basin. So prior to this project, the idea is if this is the strong influence on the wave field, we have no means to really study it without putting any seismometers out there. So this whole story could be going on and we're simply not seeing it. And so this basin offers an opportunity to get a better understanding of how earthquakes interact with these strong sedimentary basins. So we installed stations out there. This is the region, 13 broadband stations. And what you see here is they're near the Tanana River. There's no roads in this region. There's not even really a way to land a helicopter in this region. So the river provides the natural and really traditional way of getting across the region. Shown here, these are 13 stations. Some of them are A couple of them are bedrock, like this F8KN is a bedrock station on a bluff high above the river. This is a joint Pascal, NSF, and Alaska Earthquake Center supporting the telemetry on this project to allow us to see all these waveforms live, and we're open and live to the world the entire time of the project. Just to give a snapshot of kind of some of the activity on the river, there's very few people. This is a fish wheel for getting salmon under the power of the river. This is really a region where native communities from Minto Ninana have occupied for hundreds to thousands of years. This shows a shot of one of the seismometers being installed. This is Kyle Smith at an install in 2015. The culmination of some of this work is in a recent JGR paper where the setting is unique in its influence from rivers, wind, sedimentary basins, and we can pull these things apart to understand a little about in the background noise using a seismometer in a remote region to get some environmental monitoring as well as recording earthquakes that we're interested in. Here's what a site looks like. This is F3TN. It operated for 5 years without really any data losses, minimal data losses. This shows the setup, a radio antenna and a camera, station box, post hole sensor that's directly buried in the ground. And now we'll kind of get an idea of what goes on at this site from this next video. So from the work in Southern Alaska, started realizing we need to at least watch our sites and get some idea of what's going on. So we put out these sort of $100 camera with AA batteries and checked out what was going on out there. So this will give you sort of a minute of from the first winter. This is just a range of animals that were around, and you also get a sense. That's a coyote, by the way, not a fox. That's a lynx. You can see the station box here. Lynx again, walking right on top of the sensor. The sticks are actually put there to avoid certain animals from stepping directly on the sensor. And that turned out to be a good idea, as you'll see here coming up. There are 3 moose. It's a very common animal in Alaska. And so far, there hasn't been any disruption. As you can see, the sensor and site look pretty good. And then come the bears. They're very hungry. They've spent the winter hibernating, and they're also playful. They're curious. So I won't run this entire thing. We'll check out another footage later, but basically, okay, we'll watch a little of it. Basically, they're playful and they're disruptive. So the The newspaper actually featured this Nature's Vandals on the front page, documenting this sort of effect. It's a fun story. But what we'll see here is the problem is that we want to achieve high data returns, and so we need to think about the bears. So you might be saying, well, why don't you just have a stronger equipment? And that is definitely true. So in the permanent sites shown at upper left, bears are not as big an issue, but it does happen where a certain determined bear can rip off a door or do really a large amount of damage. And this is particularly challenging when you have a helicopter site or perhaps a site where other stations are relying on the telemetry. So this is a problem that we documented. I'll show one more video here from one of the sites, just giving, an idea of watching an animal in its natural curious state. It's a pretty remarkable thing. So this is this F8KN, a cub coming up to the site, one of the first to play around here. So a lot more happened at that site. But despite this adverse attention from a lot of bears, this bedrock station provided telemetry data for just over 4 years with minimal data gaps. We did get a little bit lucky, I would say, given all the attention. And if you want to read more about this, there's quite a bit of documentation for a range of projects. The moral is, if we're going to go to the effort to install a station, we need to do the effort to reduce data gaps and ensure data quality. One of these aspects in remote regions of Alaska is bears, and there are many other aspects to that station network managers face. In the interest of time, I'm going to skip this. The earthquake moose video is cool. You can check it out, but I'm going to go towards some science that came out of the FLATS project. This is a paper with a lot of authors looking at some of the exotic events that seem to be occurring within this fault zone and beneath Nenana Basin in this region. So a lot of contributions here from others. What we're looking at here, that F3 station with the movies of the bears and animals is right here. The video you just saw, that black bear, is at F8. So we're looking at events that we're really right on top of these crustal events. There are 7 events shown in this picture, including the magnitude 6 in 1995. And what you see here on the right, these are log scaled envelopes. So we take a seismogram, we take the envelope, we filter it, we take the envelope, and then we plot it on a log scale. So a normal earthquake runs along here and has a big step up at the P wave comes in, and then there's sort of a decay. So earthquakes are generally abrupt. But in this fault zone, there are a lot of different things going on. There's some events that have a 20-second or more growth and high frequency that we describe as nucleation. During some of those periods, there's actually a low frequency signal that is arising, which I'll show next. And there are also these very low frequency earthquakes. They're not abrupt signals. There are kind of fuzzy tremor-like that we interpret as this. They are enhanced in low frequency content, and they're different from ordinary earthquakes. And most of these are happening quite deep, 20 kilometers, sort of like 16 to 24 kilometers in the crust. So this is our picture. These are showing the mechanisms that are dominantly strike slip as we expect for this fault zone. And this shows the link between, this was for the station MDM, all recorded at that. All right, so here are the 2 parts of the story. One is a very low frequency earthquake on a strike slip fault system. These have been documented in subduction zones, but I don't think they have been documented as well in strike slip systems, and this one is quite well documented. So here shows vertical component stations within 200 kilometers here. It looks like kind of a brushy tremor-like signal, but things look much, much cleaner when you filter those seismograms. So here are 2 stations shown here in black and red. When you filter them at 20 to 100 seconds, you have this really simple picture that emerges that we think is telling us something really fundamental about what this source is, and actually gives us a better constraint on the magnitude as well. You can look at estimating a source time function for these small earthquakes. This is 3.7, 3.8. A normal earthquake, shown down below, may have a half second or 1 second duration, fairly impulsive. And if you take that same tool and you apply that to this very low frequency earthquake, you get some duration that's about 10 seconds. So it's an unusual event, a long duration with enhanced low frequency content, no abrupt start to the event. So this is a different kind of event. You can also look at the enhanced a spectrum of the event and see that the black curve here between 20 and 50 seconds has this enhanced low frequency content compared with an earthquake having the same magnitude and similar high frequency content in the region. So there's something enhanced about the low frequency content, hence the name. We can take these waveforms and get a very high quality estimate for the mechanism of the source. So this is shown in the beach ball here. The synthetic seismograms are in red, the data are in black. These are about as good as it gets for trying to fit 3-component waveforms for an event. So we're very confident about the geometry of this style faulting and the interpretation of left lateral faulting given its occurrence on a left lateral fault system. Second event is the 2016 earthquake. I'll have to start speeding up a little bit here, but the coverage is even better because we're pretty much on top of this event. We have epicentral distance of 5 or 6 kilometers in this case. So this coverage, if you're looking at these sort of piercing points or the aperture of your array, this is very good coverage. And again, here's a regular earthquake, or at least this section looks regular, and we have these really nice fits. But what's not regular about this event is that before the P waves, there's this nucleation signal, which was reminiscent of another event we saw in 2012. So something interesting going on beforehand. We can fit little curves to this high frequency envelopes to get an idea of the growth. We can quantify the growth that can be compared with numerical studies of simulations of how earthquake nucleation occurs. And this is shown here for one station. Just to give you some idea of the quality of the data, this is all the stations. They all show the same thing. So this is within 200 kilometers. Between these red bars, you have this high frequency foreshock signal, which gives us some confidence in exploring and really trying to understand what's going on prior to the main shock earthquake here. This shows the high frequency signal of the earthquake in the center, the low frequency blown up here on the top. And what we have is that prior to the earthquake, during this growing high frequency signal, there's a very faint low frequency signal, and we can only see it because we have stations within, 10s, 20, 30 kilometers of the event. We're right on top of the event. We otherwise would not see this signal. So it's a very powerful reminder of some of the things you can do when you're right on top of an earthquake. So here we have sort of our picture on thinking about this nucleation stage and earthquake stage. I will not spend the time to explain the sort of different interpretations of what our observations could show, but there is these two stages of thinking about very low frequency earthquakes and whether or not they transition into larger events. On to this last earthquake, magnitude 7.1 Anchorage earthquake. Giving you some setting for this earthquake, we've seen this inferred yellow outline is the Yakutat subducted Pacific Yakutat slab, or the subsurface extent. You can see that this Anchorage earthquake occurred right on this margin here where the plate is going down. The magenta lines show the contours of the subducting plate. These figures actually are slightly modified from a paper just a month before the earthquake. PhD student Vipul Silwal was actually looking at a detailed study of crustal earthquakes and historical earthquakes in this region. And so this is a figure showing that there's a lot of interesting things in the crust. This Susitna Basin, there are faulting, historical earthquakes of magnitude 7 within the crust in this same region. But the story of the 2018 Anchorage earthquake was really about emanating from the subducting slab, and of course a lot of strong ground motion effects that were felt by 400,000 people living in the epicentral region. This shows a simulation kind of again on the side of the 2018 earthquake, just to get some idea of the timing. How long does it take? When everyone in Fairbanks was feeling this earthquake, here we are 2 minutes into the event. So it's kind of a nice way to say, yeah, you're experiencing something that happened 2 minutes ago in a much, much stronger fashion in Anchorage. So this gives some idea of what this wave field complexity can arise from these basins in the area. similar to the tool we showed before for the 1964 earthquake and the Inniskin earthquake in 2016. So the motivation from a sort of outreach standpoint, by getting that simulation posted at 11:55 p.m. The day of the earthquake, it's picked up in the Anchorage Daily News the next day, and it's an opportunity to try to reach the public in a time window that's very narrow. People lose their attention on the earthquake pretty quickly, so we try to get this information out as soon as possible, realizing that we still have to perform a multi-hour simulation after we have a decent source model. So let's showcase what people have done with the new data back to the sort of scale of Alaska. I'm just going to select some highlights and point out some papers I've come across. This is the seismic network live right now, the yellow dots, and we hope as many of these as possible can stay around. This shows a paper 2018 or 19 of looking at the deeper structure. So this is at 210, 270 kilometers. The fact that we have images to resolve is really interesting. And here, these triangles show the volcanic centers. There's some sort of seemingly random volcanic centers around Alaska, but maybe the hint here is that these red or slower anomalies are pathways of warmer material in the mantle. And we see here this dark blue feature. That's a signature of the downgoing slab. We know the slab is there from seismicity, but tomography gives us this really different picture on the structure down below. So this shows one example of a study. Here's an example. The image at the right is from a paper, I think 2020 paper by Elizabeth Berg and colleagues, 1 kilometer depth, 25 kilometers. We're getting pictures and images of the subsurface of Alaska that simply wasn't possible. And the emphasis here is on the northern Alaska and western Alaska. We've had pretty good coverage in other portions of Alaska, but I would say the benefit is having all these other scientists with techniques that are evolving and developing. They now set their sights, having practiced in the lower 48 for 15 years. Alaska, at the tail end of this nationwide experiment, is the recipient of sort of the best of these techniques and where the state of the art is now. So here's a bunch of examples of different papers. They're really a big time with the data, follows a lot of projects, and it's exciting to see these come out. At the source level, here's a magnitude 7.9 offshore Kodiak earthquake. This shows the aftershock pattern. Just a reminder that earthquakes are not point sources. They don't even rupture on single fault planes. This little hatchet-shaped faulting pattern, I compare it against a figure that I rotated here from offshore Sumatra. You can see kind of some similarities about multi-faulting in the oceanic crust, but this is the kind of information that are captured. In this case, it's offshore, but just an exciting things going on in Alaska, offshore Kodiak, happening and recorded all statewide. If we look at the Anchorage earthquake special issue in SRL, just highlighting a few of these papers that have come out. If you're interested, there are more papers beyond this special issue, but nice overview on a wide range of effects here by West and others within that issue. I'm going to finish here with a video. I hope you can hear the audio. If you don't have audio, please turn it on because it's worth hearing this. This is the Anchorage earthquake live in a classroom, middle school here in Anchorage, and I'll just play it here.
Don't let yourself be convinced to do something that you know is bad, and then Ian thought to share something. Cover your mouth with your shirt.
It says cover your mouth.
Everybody okay? That was the biggest earthquake I've ever felt in my life. So we're okay. Everybody's okay, right? Stay underneath the table. Everybody okay?
So he says everybody okay, stay underneath the table. They're supposed to stay until they're told otherwise. So they're pretty much executing this perfectly. The next thing a kid says is, do we get to go home early today? So that's where the kids are thinking. But you can extrapolate from this kind of shaking what kind of damage occurred in Anchorage. There's a big deal in the largest state. Half the population of the state is there. But in terms of an outreach moment, this video is extremely powerful because as I tell any classroom when I visit them, there's always some jokesters in the class. But when you watch this class, this earthquake hits and there is total fear. Every single person is under the table immediately. And I think that's really tough to convey when you're doing an earthquake drill. But when you watch this, you get that sense of fear. Final remarks. Seismic wave field simulations require high performance computing, and they provide a valuable perspective on the wave field. They're most relevant when they're able to provide synthetic waveforms that agree with recorded waveforms wiggle for wiggle. So in order to have agreement, this requires having an accurate representation of the Earth's structure. We need a good model of the Earth. And to do that, this requires having stations throughout Alaska or whatever region you are, in particular within strongly heterogeneous regions such as sedimentary basins. These basins trap the wave fields, they have strong shaking. In order to understand that, we need to have some of these stations in these regions. It also requires that stations survive the harsh environment, whether it's snow load, cold, wind, or bears. It's a tough place to be a seismometer, but it's certainly great return. So this is a golden opportunity, an era for seismology in Alaska with EarthScope, Pascal experiments, ocean bottom seismometers, offshore imaging, and in addition to the permanent network. So I thank you very much for your attention and look forward to any feedback. You can email me and we can also, of course, go through the questions.
Mm-hmm. Thank you so much, Carl, for your webinar today. Appreciate it. Please remember that if you have a question for Carl, to please enter it into the questions chat box on your control panel. That's how we'll be taking questions today. So for starters, Felix Rodriguez Corgoza asks, for the magnitude 3.7 earthquake that you showed, what are the frequencies used for filtering that earthquake?
Yeah, so for the 3.7, the different parts of the stories are at different portions of the frequency range. So the envelopes are filtered from 2 to 8 hertz. That signal seems to be a good one for examining the higher frequency pattern. For doing the moment tensor inversion, we're typically looking at 10 to 40 seconds to get reliable long period estimates for that. For the onset of this very faint low frequency signal that happens before the earthquake, that is I believe at 20 seconds and longer periods, and for that you have to be very careful. You have to do this sort of 1-pass filtering instead of 2-pass filtering. Hopefully that answered the question, but I can also say you can grab those waveforms as well and play around with them. I encourage anyone to try.
Great, thanks. Patrick Taylor asks, are you doing any SKS studies? And if you could get a copy of your Sumatra paper?
So for the Sumatra study, I'm not sure if the link there was a figure I showed for that faulting was by Lingson Meng and colleagues from Science. In terms of, sorry, what was the first question?
Sorry, if you're doing any SKS work.
Oh yeah, great question. So yes, there's several papers that have been done. SKS splitting paper led by Amanda McPherson, which hopefully will be accepted soon. There are other groups that have looked at SKS patterns. It's a terrific place to look at shear wave splitting, and we actually have Cole Richards, a master's student here, has a thesis where he's looked at both SKS splitting and local shear wave splitting from these earthquakes. And it's really exciting for me to compare the signature of splitting from these two events to try to think about the anisotropic structure within the mantle wedge and the subduction zone, and really where it's coming from when we look at these splitting measurements.
Great. Those were the only 2 questions that we had, but I wanted to ask one, just because you've been talking a lot about how this is the golden era for seismology, and you know, with Earthscope sort of wrapping up and different things happening, what do you think is next?
Well, the exciting part to me is that you can see that we've already had, just with the data that have gone live for a couple years, we already have, new views of the Earth structure. But for me, what's exciting is that in a lot of these regions, to really image them well, we need local earthquakes. We need high frequency, high signal events to illuminate different parts of the state. And that's simply going to take time. These have only been out for a couple of years, and a lot of these regions far from the subduction zone just requires time to build up the set of new information. It's not like every earthquake we see is going to be an equal, a redundant contributor to imaging Alaska. But in addition to that, there's just new source regions happening all the time. I mean, this Kodiak earthquake is an example where, we really didn't have any idea of the capability and the style of faulting that can happen offshore. But Kaktovik earthquake, there are swarms going on. So just the nature of what the Earth tells us is that in any given time window, we haven't seen everything in the past that we are going to see in the future.
Great. There is a couple of questions about the instrumentation that came through. The first is from Justin Sweet, who asks that you mentioned that the flat stations were telemetered. Could you say a bit more about this? Was it useful? How expensive was it to implement, and was it worth the cost?
That is a good question. I would say it was worth the cost, and it was important to demonstrate there was some mutual benefit between the science objectives of the project and the operational focus of the Alaska Earthquake Center. So by having the telemetry, the data come in live and the events get seen immediately and processed along with everything else. So that's a tremendous benefit to our project in the sense that these stations come in like all the other ones. It also allows us to do science rapidly. Instead of once a year going out there to grab these waveforms, we're able to react right away. And this was, I'm not certain that we would see all the things that we saw without the eyes of all these analysts staring at these earthquakes coming in. They said, what was this? This is flagged as some X event, not an earthquake. And within a matter of days, we're diving into this story. So I'm not sure that we would have come across that without people looking at it. And lastly, to give one concrete example, we had a full year of data that would have been lost entirely because the station went out in a huge flood event, sort of a 10-year max flood event on the river. And so those data would have been gone entirely. But at least with telemetry, we have the data even if the station's gone.
Great, thank you. Yuri Starvoid asks, how is power supplied for the broadband station equipment at the permanent remote locations?
Now I'm starting to sweat because I don't know much about the power, but I'm gonna say something like less than 2 watts. Someone else could chime in there, but these are the telemetry doubles the power consumption approximately. So instead of 6 air cell batteries, we would have 12. If we had a cell modem, we'd actually have 15. So it's a significant cost of sort of doubling the cost of these batteries, but there's also a cost to get to these sites. So once you're there, and design the site properly, and you can reap the benefits. Honestly, probably having 15 batteries in a box made it harder to pull out of the ground. So it's for a bear. So there are other subtle things to think about as well.
Thank you. Stephen Hicks asks, it's kind of a long question, Carl, so bear with me. What do you think makes the Minto Flats fault zone so geologically special in terms of your nice VLFEs and precursory nucleation observations? Do you think this feature can also be seen in other strike slip fault zones if we look hard enough for them? Or is it because the stations in Alaska are so quiet and can record very small amplitude signals?
That's a great question that I've been thinking about for years now. I'm led to believe, first of all, there are other strike slip fault systems that are much better instrumented. For example, Parkfield. Um, I do not know what makes Minto Flat special, but I don't think it's just a matter of looking hard enough. I'm inclined to believe that this particular fault zone has some processes going on deep in the crust that are perhaps different from other settings. I don't have a complete list of all the fault zones with comparable instrumentation. I mean, we are talking, not only are we instrumenting a fault zone, but we're capturing events that are actually happening. So, you know, when you're within 5 kilometers of a magnitude 4, that's not that easy to do. I mean, sure, if there's a magnitude 7 and you go do an aftershock deployment, you're going to capture magnitude 4s. But this is not that. This is sort of like putting things on a fault zone where, you know, we get an occasional decent sized event. I'd be open to any feedback on this point. If you're someone who's got a fault zone that's instrumented like this and you know, is not seeing this range of events, it'd be interesting to try to understand why. But I'm inclined, I wish it was kind of a globally significant VLFE producing case in a way, but I'm still pretty happy that this particular fault zone is has got a lot of interesting things to look at.
Great, thank you. Marguerite Jadamek, sorry if I'm butchering everyone's names, but with the recent seismic work that has come out, how different are the slab models beneath South Central Alaska from previous models like the slab E115 in her 2010 paper and the more recent geometry from the slab 2.0 from Hayes et al.?
Yeah, so this is an interesting question. Alaska happens to be a place where there's probably eight or so different geometries of the subduction interface, and this information is useful for interpretations and even for perhaps designing these models. I know for sure in some regions to the east, this new slab 2.0 model is a significant change from 1.0, especially under the Anchorage region and how far it extends to the east. We know from geodetic data that the interface is quite far to the east and perhaps farther from the east from the 1964 aftershock region as well. I guess there are variations, and up until this point in time, for my own research, it hasn't been critical to choose one or the other, but at the moment I've been using the slab 2.0, which incorporates some of the shallower active source data that had been acquired. But it's important to keep in mind that there is uncertainty on the estimate of the interface. And so however it is used, we have to keep that in mind.
Great, thank you so much, Carl. We're just after the top of the hour, so I'm gonna go ahead and conclude the webinar. Thank you, Carl, for your great talk today. There's been a couple people who wrote in just to say thank you. And I did want to make mention that our next webinar will be held on March 11th, again, which is a Wednesday at 2 p.m. Eastern. And Dr. Patricia Persaud at Louisiana State University will be talking about her work in the LA Basin. So mark that on your calendars. There'll be more information to come out about that in the next few weeks. So thank you, everybody. Thanks again, Carl, for your wonderful talk, and have a great rest of your day. All right, take care.
Thanks, everyone.
Bye.